Hello everyone, welcome to the second session on database management system, in which we will discuss about the schema refinement. The overview of the session is, we'll try to understand that what are the anomalies, why do we need decomposition, what are dependencies, and how to calculate the candidate keys. First of all, let's understand that what is redundancy. Redundancy is a duplicate copy of the same data which is stored at different locations. If we talk about this relation, the example which is there on the screen, I have an example where I have a student database who are enrolled in an institution with so many different courses. If I talk about redundancy, these rows 1, 2, 3, they look quite redundant, they are exactly same. So this is something which we call redundancy. The same set of data which is repeating itself in a relation is the redundant data. So we can also get rid of such redundant data sets in our relations. So why do we avoid redundancy? We get so many anomalies due to this redundancy. One is the update anomaly, second is deletion anomaly, and the insertion anomaly. Let's try to understand that what is an update anomaly. An update anomaly is, suppose I have a redundant data in relation, and if I need to update that data at one place, I need to update in all the other copies of that relation. And if I miss updating the data in one of the copies, then the whole data will get corrupt because of the missed updation. What is a deletion anomaly? We'll get to it in the next slide. And insertion anomaly is also something which we'll try to understand here. This is the same relation which we have seen in the first slide. So we see that there are certain students who are enrolled in certain courses, and we have the faculty ID who is teaching that course, faculty name, and the fee of that particular course. We already realized that these three items, they are redundant. So let's talk how can these anomalies occur in this relation. First of all, let's see if I need to update the fee of the C programming course. The course name C, I need to update the fee from 5K to 6K. If I update the fee here and I update the fee here and I miss updating it here, it will create mismatch in the database, which is not right. So if I am updating one copy, then I have to update all the other copies of the same data. So this is the updation anomaly. Next is the deletion anomaly. So what do we mean by deletion? If I suppose in this particular database, there is only one student who is enrolled in a particular course C++. If this student leaves my institute, what will happen? I will be deleting this student from my database, which will result in losing the information of this particular course. So this is a deletion anomaly where I am forcefully losing a certain amount of data which I am not wanting to. And what is the insertion anomaly? Suppose I am introducing a new course to my institute named Java with a certain faculty. For example, there is a new course Java with faculty F3, the name of the faculty being Z and the fees being 10K. So in this course, I don't have any students yet. So what do I have to do? I have to insert the null values here where there is a student information. So forcefully, I have to insert null values to some attributes of the relation. So this is called an insertion anomaly. So we understood what is insertion anomaly, what is updation anomaly, and what is deletion anomaly. Insertion anomaly is where we are forced to insert some null values to the relation, and deletion anomaly is we are forced to lose some data because of some other data, and the updation anomaly is we need to update all the copies of the redundant data when there is updation required in the database. So, what is the solution of removing this redundancy? The solution is to decompose the tables. For example, we have splitted the existing table into the two subrelations. Splitting the relation into two or more subrelations is called the decomposition. What we did here is we have separated the student relation from the course details. Here we can see that we have two relations. One contains the student details with student ID, student name, and what course the person is doing. And the course details are the faculty who is taking the course, the details of the faculty like FID, FName, course details, course ID, course name, and the fee of that course. So what happens here? Do we have more anomalies here? No. If I need to introduce a new course called Java, I can independently do that in the second table. I can insert faculty F3 with the name Z, with course ID maybe C3, with Java as the name of the course, and 10K being the fee of that particular course. I don't have to forcefully insert any null values to the student database. Okay, suppose I need to introduce or I need to update the fee of a particular course from 5K to 10K. What will I have to do is I just have to update the one copy of this data because it is available at only one place. So we get rid of insertion anomaly, we get rid of updation anomaly. So what is the deletion anomaly? Suppose the student S3, he leaves my institute, but still I have the details of my course C2 with me. I'm not losing any details or any information forcefully due to the deletion of a particular student from my institute. I hope you understand what are the anomalies and how do we handle these anomalies. So decomposition is not really easy. Decomposition may also satisfy some properties which we'll be covering in the next videos. So we should know that what are the properties which need to be understood or which need to be followed when decomposing the relations. First of all, there should be a lossless join decomposition. Lossless join decomposition means when we're decomposing the tables and we are rejoining the tables, we should not lose any information in any case. So next is the dependency preserving decomposition, which means all the dependencies in a relation should be preserved. For example, if one attribute is dependent upon another attribute and this dependency holds in the parent relation, then it should also hold in the decomposed relations. So there should be no dependencies which have to be lost while decomposing the relations. So let's understand what are the functional dependencies. So let R be a relational schema. X and Y be the non-empty set of attributes over R. So X is functionally dependent upon Y if X functionally determines Y. Here, let me take an example where I have a relation R with two attributes, student ID and student name. What can I do here is student ID functionally determines student name. Yes, it is true. If I know the student ID or the roll number of a student, I get to know that what is the name of the student and which student is being referred. But, so if I say that S name functionally determines S ID, this is not true. If I talk about my student database, and in my database I have two students with the same name but different roll numbers, and if I talk about a student whose name is A, I can say that with A I get confused that which student I'm talking about with the roll number or SID 1 or SID 3. So this gets confusing, so I can say that this statement is not true, it is false. So it does not functionally determines SID. So X goes to Y means X functionally determines Y, or Y is functionally determined by X. If I talk about a course or course name, yes, they are functionally dependent. Course ID functionally determines course name. FID functionally determines F name. Okay, but if I talk vice versa, F name to FID, this does not hold true in any sense because there can be multiple instances of same name in a database. So let's try to understand the properties of functional dependencies. So what is a trivial functional dependency? If X is a superset of Y, then X goes to Y is always true. For example, if SID goes to SID, here X is XID and Y is also SID. So X is a superset of Y. So what do we mean here? That this is a trivial functional dependency. If we take the second case, SID, S name, functionally determines S name. So S name is something which is, we can say Y here according to this, and X should be superset of Y to determine it as a trivial functional dependency, and let's see if it holds true. Yes, SID S name is the superset of S name, so we can say that this is a trivial functional dependency. In the next case, SID S name is determined by SID S name. Even in this case, SID S name is the superset of SID S name. So this is also called the trivial functional dependency. And what about the non-trivial functional dependencies? If SID goes to S name, in this case, SID is not the superset of S name. So I can say that this is not a trivial functional dependency. CID is not the superset of C name. So this is not a trivial functional dependency. But yes, if I say that FID, F name functionally determines F name, here, yes, it is a trivial functional dependency because FID F name is a superset of F name. I hope you understand what is trivial functional dependency and what is non-trivial functional dependency. So there are some other properties of the functional dependencies. One is the transitivity. It is one of the properties of the functional dependencies. Let's see all the properties one by one. If X functionally determines Y and Y functionally determines Z, then X functionally determines Z. If X functionally determines Y, then XZ functionally determines YZ. If we make a superset of X with any particular attribute and we add the same attribute to Y, then this relation holds true. If X functionally determines YZ, then X functionally determines Y and X functionally determines Z. And if X functionally determines Y and X also determines Z, then it functionally determines both of these attributes, like this. So these are the properties of transitivity which should hold. Next we come to the attribute closure. What is an attribute closure? Suppose I have an attribute X, I represent the closure with a plus sign on that attribute which represents the attribute closure. So the set of attributes that are functionally determined by X are called the attribute closure. Let's try to understand. Suppose I have a set of functional dependencies for a particular relation. I have a relation where I have certain attributes A, B, C, D, E, F, G. For example, I have a relation with these many attributes, and this is a given set of functional dependencies over the relation. So what is the attribute closure AB? What is the AB closure? Okay, let's try to understand. If I have to talk about AB, I need to understand that which all attributes are functionally determined by A and B. Let's try. First of all, AB is functionally determined by itself. So we add A and B to the list. After that, AB also determines C. This we get to know from this particular functional dependency. So we add C. So now we also have C in the list. From C, what is determined? D. So I can say D. From D, is there anything which needs to be added? No. From any of these, anything can be added? Yes. From B, there is one more functional dependency. So I can add G to the list. So what do we understand here is, so the attribute closure of A, B is A, B, C, D, G. If I talk about AF, let's try to calculate the attribute closure for AF. First of all, I need to add A and F to the group. Okay, so from both of them, A and F, what can be added more? From A, we cannot find anything which can be added because there should be A and B both, from where we can add C. But here I don't have B here, so I cannot add C. But I have F, and this is a functional dependency which can add B to this pool. So I add B. Now I have A and B, with which I can use this functional dependency to add C to my pool. From C, I can use this functional dependency to add D. From B, I can also add G. Is there anything which is left? No. So this is the final set of the attributes which are functionally determined by AF. So the closure of AF is A, B, C, D, F, G. I hope you understand how to calculate the attribute closure. To take another example, let's calculate the closure of attribute C. I can say the attribute closure of C is, first of all, C itself, it has to be added. From C, I can add D, and from C and D, can I add in anything else? No, because there is no functional dependency. So now let's see what is a candidate key and how the candidate keys are calculated. Currently we have understood that what is attribute closure. Here we will see how to calculate the candidate key from the attribute closure. So let R be a relational schema. X is a set of attributes over R. If X closure determines all the attributes of the relation, then X is called the candidate key or super key of relation R. Let's understand what does this mean. For example, I have a relation with 5 attributes A, B, C, D and E with the set of functional dependencies F equal to AB to C, C to D and B to E. So, if I talk about the closure of AB, it comes out to be A, B, C, D, E. How? As we calculated the closure in the previous slides. Now, my relation has 5 attributes A, B, C, D, E. And in the closure of AB, I have A, B, C, D, E, which is equivalent to the number of attributes which are there in the original relation. So, if the closure of certain attributes represents all the other attributes of the relation, then we call it a candidate key or a super key. So we can say that AB closure, AB is a candidate key or super key. Now we need to understand that what are the prime attributes. So the attributes that belong to a candidate key are the prime attributes. So in this case, we have a candidate key AB. So how many prime attributes do we have? In the candidate key, we have two attributes, A and B. So in this relation, I have two prime attributes, A and B. There might be possible that there can be more candidate keys which we need to calculate. For example, I take C closure. What does that mean? It will add C, it will add D from this, nothing else. Is CD equal to ABCDE? No. This means C cannot be the candidate key of this relation. If I talk about D, what does that mean? It will add B, it will add E from this, it will not add anything else. Is BE equal to ABCDE? Still, no. That means B also cannot represent the candidate key or all the attributes of the particular relation. If I talk about ABC, yes, this represents all the attributes of the relation R. But this is not the candidate key. This is a super key, because in this group only there is one more minimal set which can independently represent all the attributes of a relation R. So we can say in this relation R with attributes A, B, C, D, E, we have only two prime attributes which are A and B, because AB forms the candidate key of relation R. Let's try to understand this with the help of another question. Suppose we have a given relation A, B, C, D, E, F with functional dependency set AB goes to C, C determines D, D determines E, and C determines A. So let's try to find out all the candidate keys. Let me find the A closure. Am I able to get anything from A closure? I can get only A. From B closure, I cannot get anything. I can get only B. From AB closure, I can get A, B. From AB, we get C. From C, we get D. From D, we get E. So is this sufficient? Okay, I tried to verify this with the original relation. I have A, B, C, D, E and F in the original relation, and here I have only A, B, C, D, E. So what is missing? We have F, which is missing. So are we able to reach F from any of the functional dependencies? No, because F is missing from all the functional dependencies. So what we have to do now is, so we are very clear from this fact that if F is not there in the functional dependency set, we cannot reach F in any case. So what we need to do is, we will add F in the candidate key itself. So if I do A, B, F, it comes out to be A, B, C, D, E, F, which determines all the attributes of a given relation. And so this is the candidate key. Similarly, we can find the other set of candidate keys if possible, and we are sure that all the candidate keys will definitely contain F in them, because F cannot be reached from the functional dependency set. So this is all with the candidate key. I hope you enjoyed the video. For more such videos, please log on to hitbullseye.com. Thank you.